Let's begin talking about net force. I encourage you not to write everything down. I encourage you to learn what you need to know, and if you think you need to write something down so you can learn it, then you go right ahead. But please do not write word for word what I put on the screen. I know you've been trained to do that. Stop it. You should think of what's on the screen as my guide for a discussion. It helps me to keep the conversation in the right track here. So, in the expression F equals ma that I know you learned in grade 10, the A can be interpreted as the total result acceleration which a body receives when acted upon by some total force whose magnitude and direction are given by F. And fancy words for A is the resultant acceleration of a mass that has a net force applied to it. The F in FA is the net force. That's what I'm saying. Are you guys writing everything down?
No.
The F in F equals ma is the net force. Now when I say the net force, what does that mean? What does it mean?
Net total force.
Of, like,
All the combined forces.
add up all the forces, and are they vectors? They're a force, so yes. Right? Add up all the forces, and that is your net force, right? Could some of them be in like perpendicular directions or even weird kind of directions? Absolutely. And that's what this slide's about here. Since force is a vector, and again, I'm going to be posting these up to Schoology like right over here. Since force is a vector quantity, the total force acting upon an object is the vector sum of the separate forces that are acting. It is usually called the net force. The net force is the sum, vector sum of all the forces. Do you need to write down F net equals F1 plus F2 plus F3? Is that a formula you need to know? No. What am I just saying? The net force is sum of all the forces. There might be 1, there might be 2, there might be 3, there might be 4, there might be 100,000 of them. Dot, dot, dot. Ellipsis is what it's called. The net force is the sum of all forces. Your job, yesterday we drew force body diagrams, free body diagrams. Your job is to figure out what all those forces are and to come up with the sum of them. And then that's going to lead us to, now I always say that this formula here is what I call the bridging formula. Okay? There's kinematics, which is how objects move. There's the Vs squared equals Vx squared plus 2AD, all those crazy formulas. And then there's F equals ma, right? And then there's all the force formulas. And the F equals ma is kind of like the gatekeeper. It's what gets you from forces to velocity and accelerations and distances and all those things, right? You got to go through F equals ma. That's the only way. That's the force one, and there's the acceleration. That's the key to getting all the kinematics ones. Here's the most ridiculous example ever. Do not write it down. Johnny and Billy are playing tug-o-war. Tug-o-war in honor of St. Patrick's Day coming up. Each one is pulling with 75 newtons, and this game will go on forever. Anyone winning? What's the net force? Big fat 0. We got plus 75 and we got minus 75.
Someone's got to win eventually.
Not if the forces remain constant. Now, if all I gave you was like, I say, is this object moving? Well, no, it's not, right? But if all I gave you was this, if all I gave you was that diagram, remember this from grade 11? Can you tell me, is this object moving?
Yeah, maybe, depending if it's already moving.
Very good, Steve Droge. Do you remember that stuff? Maybe, if it's already moving. What if Johnny and Billy are playing tug-of-war on a moving train? You know, maybe they're reenacting James Bond on top of the train and they're fighting over a Snickers bar or something. It's a really large Snickers bar. That's why they want it so badly.
Is it really, like, long?
Yeah, oh yeah, it's like giant Snickers bar. Product placement for the movie they're making. In the sequel, they figure out they should not fight over the giant Snickers bar. They should pull on it in the same direction. They're each pulling with 75, oh, now it's a sledge, trust me. Each one is pulling at 75 newtons, so what's the net force? 150. Is any of this hard? No. Certainly don't need to write it down, right? You can do 75 plus 75 in your head. You get this. This is review. Okay, now, let's talk about friction. In real situations, friction is often a force that reduces the net force. Results in the formula F net is equal to Fa plus Ff. Now really, all this is really just a rewrite of F1 plus F2, right? That's all it really is. It's just more specific, well said. Right? It's F1 is the applied force and F2 is the friction force. Mr. Bennett, students often say to me, shouldn't that be Fa minus Ff? No, because the net force is the vector sum of all the forces, and it's just that the Ff happens to be negative. So think of it that way. We call it Ff, like all forces, a vector, so it being in the opposite direction, it will have the negative sign associated with it. So we're always doing vector addition for the net force. Have I lost anyone? Here's a quick example. Suppose a 10 kilogram object is being accelerated by a 10 Newton force. The force of friction is 6 newtons. What is the resultant acceleration? This would be something that I would expect you to be able to do at the early part of grade 11. You can probably do it in your head. If you were to write it out, and maybe I need to give you time to write that question down, do I? Okay, I'll pause. Okay, so what would you do here? F net equals Fa plus Ff. The net force is, the applied force is 10 plus minus 6. I think Quinn said it. We have a net force of 4 newtons. What is the resultant acceleration? Newton's law, F net equals ma, the bridging formula. 4 equals the mass is 10, a 4 over 10, 0.4 meters per second squared. And if you had some time or something or other, you could figure out distance or any of those other things, right?
Hello, Paulson.
Hello, Nate. See you later.
All right.
Would you agree that that's more or less grade 11 easy to medium quick style question? Right? Pretty straightforward. Obviously, we're going to take it a step further. All good? Everyone's good? Yeah? Okay. Here, I'm going to go the opposite way. Here, we're going to talk about what force of friction is acting. So I'm going to sort of have to go backwards. Okay? What do we have? We got the mass, we got a velocity, I got time, and I got another velocity. I'll give you a moment to jot that one down, and then we'll figure out a plan of attack. One thing that may help some people when you're doing problems like this is to sort of come up with a bit of a plan, right? So I got to find out what force of friction is acting. So I'm going to need Ff as my final answer. And how do I get to Ff?
What's that?
Friction force.
Okay.
Right? So what's going to get me to Ff? Well, if I know F net, now hold on here. Are there any other forces acting? Maybe we should draw a picture. A 3 kilogram object is going 5 meters per second. 4 seconds later, it's traveling at 2 meters per second. What force of friction is acting? You know what?
So each second is kind of slowing down.
Yeah, well, it's not kinda.
Well,
It's going 5 and then 2, right? So it is slowing down. So what are the forces acting? Just friction. Now, someone might say, well, isn't it happening on Earth? There should be gravity. and it sounds like it's on a tabletop and there should be a normal force.
Yeah, but if it's equal, it doesn't matter.
They sort of just don't really matter, right? They balance out. It's like, do they have any bearing, any effect on the problem at all? None. Technically, you should put them in there, your free bet again, but okay. So in other words, what is my net force? Well, it's my friction force. So how do I get F net?
Acceleration.
I need MA. I know the mass, so I need acceleration. How am I going to get acceleration? You could do that, which is really equivalent to this one, right? So there's your plan. There's your attack. Three kilogram rotor is going 5 at the start, so my initial velocity is 5. What's my final velocity? 2. Solving for acceleration, that all happened in 4 seconds. Right? 2 minus 5 over 4, right? As Steve said, delta V over delta T. That's going to be minus 3 over 4 or minus 0.75 meters per second squared. Go back to the plan. Once you've got acceleration, mass, get our F net, right? F net is equal to MA. 3 times minus 0.75. I think that's minus 2.25. And we've already agreed that that is the friction force. Do you guys know the 3 dots in a triangle symbol? Do they use that in math anymore?
No, I don't know.
Someone said yeah. Is that you, Aaron? Yeah. It means what? Therefore, yeah. Therefore, the friction force is minus 2.25. Why? Because that is the only force acting. Right? Hey, that was actually pretty easy.
Yeah.
Again, this is meant to be a bit of a review, get you back into thinking about these kind of problems. None of these are going to be particularly difficult. We'll save that for the next day. Okay. Does this one give you some fear? That's the word I was looking for. Force of 50 newtons is applied to a 10 kilogram snow sled at 30 degrees above the horizontal. The force of friction present is 18 newtons. I wouldn't say that it should give you any fear, but this is probably the upper level of what many of you have solved up to now. Would be my guess. Okay. The force of 50 newtons is applied to a 10 kilogram snow sled at 30 degrees above the horizontal. The force of friction present is 18 newtons, and we need to find FH, F net, and A. I've given you these steps, the outline plan here. What does FH stand for? Anybody remember? No, it's not the hypotenuse. Horizontal, the horizontal component, right? It's this guy right down here. The horizontal component. How much of that 50 newtons is actually pulling sideways? How much of that 50 newtons is actually pulling sideways? And I heard someone over here talking about trig and stuff. It's because the FH is adjacent, right? It's going to be F cos theta. Is the FH always going to be F cos theta? Usually. In fact, 99.9% of the time it is. Because almost always they give you this angle down here, right? They're not going to give you the angle up there. That doesn't make a whole lot of sense. It's always the angle at the start. So it's always usually going to be 30 degrees, unless it's 30 degrees from vertical, which you occasionally see. So just be aware of that. So in this case here, it's going to be 50 cos 30. Make sure you're in degrees. And I get 43.3. Is that what you got? So of that 43, of that 50 newtons, 43.3 actually goes into pulling it sideways. Where does the rest of it go? Do you remember? What's this guy called right there? Vertical component. What does it do? It's lifting it up, isn't it? Right? Would it be 6.7? Would it be? No, because this is 43.3 sideways. You would need some other number lifting it up to give you a total here of 50, right? It'd be like 50 squared minus 43.3 squared would be that squared, right?
Yeah.
So it's not just going to numerically, like, it's not going to be 6.7. Doesn't ask for that, though, so. So there's our horizontal component. Now, they want to know what the net force is. So now, again, you can't ever have a formula just for net force because it always depends on what's in the situation. So in this case, the net sideways force is going to be FH plus FF. $43.3 minus 18. $25.3. What if the horizontal component wasn't enough? What if the horizontal component was only, say, 15 and the friction force was 18? What would happen? It wouldn't move, right? You got to overcome friction. Okay, so now we got the net force. Next step to find the acceleration. F net is equal to ma. 25.3. My mass is 10. So for acceleration, A equals 25.3 divided by 10, or 2.53 meters per second squared. Remember back in the good old days, of grade 11, when 2 steps was like a hard problem? And you didn't have to worry about organization of solutions? Zach? Organization of solutions is going to become increasingly more important. When we do projectile motion and there's 9 steps, it's going to matter. For those of you that are a little bit on the messy solution side, it's time to start cleaning that up. Part A, Part B, Part C. I'm going to even make the problem longer. If it started from rest, find its displacement after 4 seconds. I'm going to put this all on one slide so I can see it all. If it started from rest, find its displacement after 4 seconds. Again, this F net is equal to ma is that bridging formula. It gets us to those kinematics. So now, find the displacement after 4 seconds. I've got the acceleration. And I've got the time. I want to know d. It started from rest. Vi is equal to 0. Like so. Any questions or issues, concerns? How are we feeling about that? Again, it was kind of designed to take you through basically everything in grade 11 in about a half an hour. Thanks, man.
I think we all learned a little back.
Some R&R, yeah? Remember, use this as your guiding principle. Quick. Spoiler alert. Yeah.
Still throwing it out there.
I remember seeing it in the theater, you guys, in 1977. I was in Wyoming. We are done.